Hello, bonjour, I'm Ahmed.
Hi, bonjour. My name is Muhammad Hanif Najwan bin Washam.
Hello and Assalamualaikum warahmatullahi wabarakatuh. So my group will explain and talk about topic system break at MRT. So enjoy the video and let's learning together. Every moving part contains energy known as kinetic energy. When the train running, it also creates kinetic energy and needs to be removed in order to stop the train. The purpose of the braking system is to perform control reduction in the velocity of the train either to reach a certain lower speed or to stop at fixed point. The railway braking system is known as the compressed air brake system. It is a system where the air drawn into a compressor and stored in the main reservoir. Compressed air from the main reservoir is distributed along the train through the main reservoir pipe. On each vehicle, the pipe is connected through a triple valve to an auxiliary reservoir which stores air for use on that vehicle's brake system. The air brake is standard and used by railway all over the world. It is based on the simple physical properties of compressed air. In 1869, an engineer named George Westinghouse invented the first triple valve brake system after considering the importance of safety in the railroad industry. However, his system worked the opposite way of a direct air brake system. Air brakes work on the principle of conversion of energy. Generally, in train while it's moving, is produced kinetic energy. This kinetic energy must be reduced to make the train stop. The air used to reduce kinetic energy by converting it into heat energy. The system mainly consists of compressor, main reservoir, control valve, brake pipe, triple way, auxiliary reservoir, brake cylinder and brake pad. The compressor takes air from the atmosphere and compress it. This compressed air is sent to main reservoir. Through the control valve, it passes to auxiliary reservoir. These are air supplied to brake cylinder through the triple valve. The brake valve is controlled by the driver, who can control the intensity of brake. According to the requirement, when the driver pushes the brake or apply the lever, the pressure in the reservoir decreases, which pushes the brake pad towards types and apply brakes. So, today we will explain about the brake system mode for train, and then for the train have 5 brake system mode, which is first is service brake, and then emergency brake, parking brake, rescue brake, and conditioning brake. And then we will explain on the next slide.
Okay, for the first braking system is service brake. Service brake commonly used in the normal operation of the train to reduce speed of the train, hence slow down the train. It used the electrodynamic brake (ED) to trigger the braking system. Electrodynamic also to minimize the wear of brake pads. This brake force will distribute to all parts of the train, hence stop the train. The maximum allowable service brake is 1.1 meter per second square, with a jet limited with 90% brake pressure applied to stop the train. Electro-pneumatic brake EP will use only if the braking force that produced by ED is not sufficient to slow down the train. Extra brake effort will be supplied by EP when the speed of the train is above 50 km per hour to 70 km per hour, depend on the load condition. Next, emergency brake. This braking system uses only pneumatic brake, which is air for the safety reason. For example, if the train is in the critical condition where the electricity is not sufficient enough to operate the train or drive the train, the service brake will not functioning well because it requires electricity to energize the electrodynamic and electro-pneumatic brake. So we need to use only purely pneumatic brake, which is air, to stop the train. That's why we choose pneumatic brake for the emergency brake. The emergency brake rod in the passenger compartment is used by the passengers to apply the passenger emergency brake. Each passenger compartment has 2 emergency brake rods. When the emergency brake rod is engaged, the safety circuit is quickly opened, hence trigger the emergency brake. At the same time, the dash-mounted HMI will on the buzzer alarm to notify the driver that the passenger emergency brake has been engaged. After the train has come to a complete stop, the operator must insert the square key into the passenger emergency device and turn the key to reset the passenger emergency rod in order to release the emergency brake. During this application brake, all the jerk limitation is cut out. This means the train will be slow to 0 km per hour without a jerk. Maximum deceleration of emergency brake is 1.07 meter per second square with purely air brake applied.
So, I will explain. The next brake mode is parking brake. First, parking brake, integral part of the friction brake actuation system. It is spring applied and air release. Parking brake start applying automatically once the brake reservoir pressure drops below a certain threshold pressure. Next, parking brake totally release when the pressure exceeds the parking brake release pressure of 4.8 bar. The parking brake holds an AW4 loaded train on the maximum gradient of 4% for unlimited time. All axles of the train are equipped with parking brake. If parking brake is applied when train is in the motion, the OCC gets a signal about this failure, and the train able to move to the next station with reduced speed in order to avoid the damage of the brake disc and brake pads. Here you can see how the parking brake is applied. The next brake mode is rescue brake. Rescue brake is function enables release and reapply of emergency brake and parking brake, as well as braking function during rescue and shunting operations. Also enables shunting by locomotive using locomotive brake pad pipe to control the brake in the shunt train, as well as to apply emergency brake in the shunted train while shunting. And then to provide sufficient air supply for rescue and shunting operation, the MRE pipe is coupled between the train and the locomotive. Applied emergency brake and parking brake is in the shunted train will be released when the brake pipe of the locomotive is coupled to the rescue pipe of the train through the coupler. And when the brake pipe of the locomotive is pressured with 5 bar, which is the normal operation pressure of the locomotive brake pipe. In this slide, you can see the rescue brake before coupling and the coupling, which is the rescue operation. So after coupling, the rescue train will control of brake system of the shunted train. Next, I will talk about the wheel slide protection. Wheel slide protection is known as WSP is active during service and emergency braking. WSP function for the friction brake is performed on a per bogie basis. The WSP function of the electronic brake control detects and corrects wheel slide by controlling the brake effort, and so prevents the wheel from blocking and developing flat spots. A speed sensor and a pole wheel mounted on each axle are used to monitor the axle speed. Two methods of slide protection detection are employed to determine that sustained low adhesion condition between wheels and rail exist. First, excessive deceleration of an individual axle. Second, speed difference between each axle and the accelerating at the highest speed. The efficiency of the wheel slide protection for the emergency parking brake is greater than and equal 85%. The efficiency means the grade of utilization of the actual available friction coefficient in case that due to lower friction level while slide protection is applied. When the wheel slide protection algorithm determines that the adhesion condition have returned to the normal, then the system returns to its original state and regular ground speed testing is stopped. This slide shows the circuit of wheel slide protection. As we can see, wheel slide down valve units are mounted adjacent to each bogie to minimize the reaction time of the wheel slide protection. The WSP module comprises valves to control the brake cylinder pressure and a pressure sensor. It is connected to the drive or brake control unit. In case of wheel slide protection intervention is necessary, example due to track condition, the brake cylinder pressure is down regulated by the valve to reduce and prevent wheel slide. The brake cylinder pressure at the outlet of the WSP unit is monitored by a pressure sensor. For the pressure sensor and switch, a pressure sensor is used to detect any pressure values. The pressure is converted into an electrical signal where the amperage corresponds with the pressure. The pressure range of 0 to 10 bar is converted into an electrical signal of 4 to 20 milliampere. A pressure switch only delivers an on or off signal when reaching a certain pressure threshold.
Minimum emergency brake rate MEBR. MEBR calculated cycle every 32 milliseconds in each DBCU. This calculation takes into the following condition: state of isolation code plus A01.A-S01 plus R00.1-S01 and plus A01.2-S01. Next, available pressure in braking system plus A01.A-B03. Next, MEBR, conditions of other DBCU. Furthermore, correct transformation of CB pressure into C pressure. Lastly, result of DBCU component test concerning the emergency brake. MEBR cannot reach if the calculation gets a result that the emergency brake is not available in more than 2 bogies. Okay, next, load detection. For the first load detection is service brake. The load is detected by the means or average of the pressure sensor plus A01.A-B02/B12. It usually monitors the pressure in the air bellows and transmits the data to the CCU and DBCU. Total braking effort is applied according to actual load. A default load value load AW4 is delivered if an erroneous load signal appears. The next load detection is emergency brake. The load correction is done pneumatically by the relay valve plus A01.A-T01/T11. Okay, for the next one is warning signal to OCC. These failures will send warning signal and trigger the OCC. First, the minimum emergency brake rate MEBR is not available. Second, the isolation of one friction brake. Third, the pressure in the main reservoir is too low for the normal operation. Fourth, the brake pressure of one single friction brake is too low. Fifth, a spring deflated in one car. And lastly, serious fault of one single friction brake.
The control rescue brake is referred to the circuit. That is, you can see this in the circuit. The rescue brake is controlled by means of the traction brake controller. The traction brake controller controls the valve plus A03, KO2, KO3 and KO4 according to its set position. For the traction brake controller in drive position, you can see the valve KO2 opens. Pressure is fed into the rescue brake pipe and the pressure in the rescue brake pipe increases. Pressure is fed into the rescue brake pipe as long as the traction brake controller is kept in drive position until the limit of 5 bar is reached. As long as the traction brake controller is in drive position, the brake keeps releasing until they are completely released. For the traction brake controller in brake position, the valve KO3 opens and vents the pressure in the rescue brake pipe. The rescue brake pipe is vented as long as the traction brake controller is kept into brake position. Brake keeps accelerating until maximum brake force is reached. Traction brake controller in closed position. The state of the brake is kept. Release brake remain released and apply brake remain applied with their set brake effort. Traction brake controller in emergency brake position is the valve KO4 closes the rescue brake pipe supply and vents the complete pressure in the rescue brake pipe. This emergency brake applied. To set a certain brake effort or deceleration, the traction brake controller has to be put to brake position until the required rescue brake pressure is achieved. Then, put the traction brake controller to closed position to keep the commanded brake effort or deceleration. The rescue brake pipe pressure can monitor on surface pressure gauge GOO P or 1.
Okay, this graph shows the pressure level in rescue brake pipe, pilot's pressure CV1 and brake effort. As we can see, when the brake effort is start to apply, the pressure will be reduced while the pilot pressure is increased. So, the more brake effort, the decrease the pressure. Okay, for this graph, it shows the rescue brake control. These two graphs is connected to each other. As we can see in the first region, the train is moving in the normal condition, which means the brake effort is 0 and the pressure in RBP is the highest. Next, we move to the next region, which is brake. When the brake starts to apply, the pressure in RBP also start to reduce, makes the speed of the train also start to reduce. Next region is coast. When the brake effort is applied with a constant value, the pressure in RBP also constant, makes the speed of the train also constant. The next region is drive. When the brake effort is start to release, we can see the pressure in RBP start to increase, make the speed of the train start to increase. And the last region, we can see the brake effort is 0 and the pressure in RBP is the highest and the speed of the train is back to the normal speed as the first region.
We start to the procedure of rescue or shunting train. First, couple the healthy train to the defective train. Put traction brake controller in the healthy train in full service brake position. Full isolation code GOOASO2 to close position on the train and in the defective train as well as in the healthy train. Where the train is not coupled, and put the isolation code GOOASO1 to open position on the train which is in the defective train as well as in the healthy train when the train is coupled to the other train. Activate the rescue brake by putting the operation code GOASO3 to open position in the driver's console of the healthy train. Tow or push the defective train to its desired parking position and then put the traction brake controller in emergency brake position. Next, deactivate rescue brake by putting the operation code GOOASO3 to close position in the driver's console of the healthy train and then put back the rescue code GOOASO2 to open position again on the train and which is in the defective train as well as in the healthy train where the train is not coupled. And then for the last, uncouple the healthy train from the defective